and undersampling and all that. So we were doing a reminder of what sampling is. And here we have a summary. So let's say that you have these. So we have this x of t, that is a continuous signal. And then we want to produce a discrete signal. And as we were saying, the discreteness in this case is in the space or in time. It is not in the continuous value. So the values that the signal takes are still continuous, but in time we have steps. And these steps, we mentioned that they are determined by a sampling period that is called Ts. And then this step can be on this, this process of converting a continuous signal into a discrete signal can be decomposed in two steps. So the first one is multiplying by a train of deltas. And the second one is converting this train of deltas, this multiplication that is here. This multiplication there still has a continuous nature. So this is still something that depends on t. And then we have to convert it from continuous to discrete. And after that, it depends on m. Okay, so this is, let's put it. So after the conversion from continuous to discrete, we have something that depends on it. And then here what we have is the opposite process. So first it converts from something that depends on n to something that depends on t, and then you apply a low pass filter to recover the original signal. Okay, so far so good. Okay, so let's see. This is in real space. So let's see what is happening in Fourier space. Okay, so let's concentrate on this process here. So that is the one that we are interested in. So let's say that we have an x of t. So we have x of t that is multiplied by a train of deltas. So in Fourier space, we now do the Fourier transform of this equation. And the Fourier transform of that says that we have the convolution of these two Fourier transforms. Let's put the hat to denote that we are in the Fourier space. Okay, so let's see how the different components look like. Okay, so this is the modulus of x of j omega, and this is omega. And it doesn't repeat, it goes now from this omega maximum, and this is minus omega maximum, to infinity. It is 0. The other one is this one. So this one here. So let's do it in different color. So this one here, the Fourier transform, is something like this. So this is omega. This is modulus of phi a omega. And it is separated as 1 over Ts. And for the moment, we don't care about the amplitude. So let's keep the amplitudes to 1. So now we have to make this convolution. So this convolution is very clear. So what we have is the Fourier transform of So we have the Fourier transform of the x that has to be convolved with all these deltas. So that means that we have to copy to every one of these positions. Okay. And then we have here omega maximum, and this is minus omega maximum. What about this point? So this is this point here. So what about this point here? Okay, so this is so this point is 1 over Ts minus omega maximum. Do you agree? Okay, so let's see at which point these two spectra overlap. So we have a copy every 1 over Ts. So we have a copy every 1 over Ts. And the same as 2 over Ts and so on. Okay, but let's look at this one. So let's see at which point it overlaps. So it overlaps at here 1 over Ts minus omega maximum, and it has to be equal to omega maximum, or it is the same. 1 over Ts is equal to twice omega maximum. And here, yeah, probably I'm missing some 2 pi somewhere, but I don't care. So let's put it. I feel bad if I don't put it. So we need 2 pi here, and this is twice 2 pi, and this is 1 pi. So we are missing a 2 pi. Okay, so or pi or 2 pi. Okay, so this is what? What is that? That is the frequency associated to the sampling rate. Okay, so this is omega sampling. And omega sampling at 2 omega maximum is these two spectra, these 2 points are the same one. And what happens if omega s is larger than 2 omega maximum? Okay, so let's draw the spectra at this point. So the spectra was red, was blue axis, and red coordinates. So at this point, this is what we have. Okay, so what happens if the sampling rate, the sampling frequency is larger than twice the omega maximum?
There's going to be aliasing.
That
They're going to overlap and there's going to be.
if it is larger, what is this value here? This is omega s. Then if it is larger, then they separate. Okay, so if it is larger, then they separate. So they are equally width. So this width, this one here is still the same. This is still the same. But now omega s is farther away. Omega s is farther away, so they don't overlap. And what happens if omega s is smaller than twice omega maximum? Then they overlap. So the width is still the same. But now omega s is smaller, so the two spectra overlap. Okay, so omega s, the sampling frequency, controls the relative position of these two spectra. And then when we convert, still we are in a continuous frequency world. All these are continuous frequencies. And eventually, when we convert to discrete, okay, so we have it here, and now we convert to discrete. So now we are in the discrete world. So we have here the continuous to discrete operator. So omega s becomes 2 pi. So omega s becomes 2 pi. So here we have a copy. Not too good at making stories. This is pi. So it is something like this. And this would be a module of x of. So this is the Fourier transform of the discrete sequence. And here again, so omega s here, let's do it in real. This one goes to there. And here it is also the same. So this omega s always goes to 2 pi. Okay. So omega s goes to 2 pi, and then we have pi, and then these spectra seem to be smaller in the discrete domain, in the discrete frequency domain. Actually, we can compute what is the frequency. So any frequency in the continuous goes to is that pi? No, probably this one, but it is pi divided by. So this is the relationship between the two. I hope I did it right. No, it is not right. The right one is this one. Is this one. Okay. So we can convert any continuous frequency, and this one, just a reminder, this is pi f. Pi f. Okay, so this is in f is in hertz. Omega is in radians per second. And this omega is radians per sample. So we have the units of everything there. Okay, good. So it means that apparently, if we increase the sampling frequency, so we take more samples, apparently in the discrete Fourier transform, the spectrum seems to be narrower, and that makes sense. So let's think of a signal. So let's say that we have have, this is time, and we have a signal like this. So this is x of t. And we take very few samples. If we take very few samples, so let's say, for instance, we take this one, and then this one, and then this one, and then this one. So it has some associated frequency, but now let's say that we take many, many more samples. So we take this one, this one. Which of the two signals seem to be faster or slower in terms of discrete signal? The green one or the red one? Which one is varying more smoothly? The green one. The green one is varying very slowly. That is the slowest. So if it is the slowest, that means that its Fourier spectrum has to be more concentrated to the origin. Do you agree with that?
Yes, because you are making more, taking more samples.
Yeah. So it seems that everything seems to go in the right direction. Okay, so let's now do all these. And the problem we will address now is the following. So we have a discrete signal. So let's say we have a discrete signal. Now this is n. And we have this signal that has been sampled with many, many samples. And let's say that we do a downsampling by factor 2. So if we make a downsampling by a factor 2, or by a factor n, let's do it n equal 4 or equal 3, for instance. We are taking this one samples. So now we are going from a signal that has a sampling period that is yes, and we are transforming it into an x prime, so another representation of it. Another representation, let's do it in different color. So we are having x prime, that has the same pixel sampling period, but now multiplied by a factor of n. And then this is the n. So we are doing a downsampling of a digital signal. And we can think of this process in the same way as we did for the continuous to discrete process. So we have a signal that is x of n, that is multiplied by x ray. But now this is pi of n, and the separation of this. Let's wait. This separation is n now. And we produce a new signal, that is the red one, that is x prime. So the Fourier transform of this one will be Fourier transform of this convolved with the Fourier transform of the plane of classes. It is the same process that we had before, continuous to discrete, but now in the discrete space. But it is exactly the same process. And the same problems arise that, okay, so the Fourier transform of this one is a set of impulses, and then we have to make copies of this one to this other set of impulses and so on. So we have exactly the same problems, But now only that everything occurs in the discrete Fourier space. Okay, so let's see all these now in the slides. Okay, so the slides to see all this process. And here we have an example of the aliasing. So we have this image that is discrete. We do a downsampling by factor 2, so n is equal to 2 in this example. And if we don't take care, then the spectra overlap, and then we have these jaggeds in the grid in front of the train. Okay, so these jaggeds, they don't exist. The grid doesn't look like this, it looks like this. But because of the aliasing, we have this pattern. Okay, so yeah, so this is just a reminder of how we can do that. Actually, this process of taking one sample every n is called decimation. So the downsampling, if you want to do a downsampling, so we have, let's make it bigger. So this process alone, this process is called decimation. And if you want to do a downsampling, then you know that this spectra may overlap. So what you do normally is you apply an anti-aliasing filter, and then you do the decimation. And both together, it is downsampling. So the downsampling is the anti-aliasing filter and the decimation. Okay, so yeah, let's remind a bit again before we get further. Okay, so let's see what will happen. So yeah, we have a Fourier transform. We have a Fourier transform of this signal. So let's put again the model with decimation on it. So we have the decimation. We have the decimation here. Okay, so what will happen? So we have the Fourier transform. We have the Fourier transform of this. Let's say it has this shape. This is omega, it has this shape. Okay, and it goes to omega maximum. And we know that there are copies. For instance, at 2 pi, at 2 pi, we have another copy of the same spectrum. And at minus 2 pi, we have another copy. Okay, so now we do the decimation by a factor n. What will happen with the spectrum? So it's the same actually. So what will happen with the spectrum? It will be enlarged by a factor n. So it will be enlarged. So now this point is n omega maximum. And this point, what was this point here? So this point here was 2 pi minus omega maximum. So it goes So this is 2 pi. So this copy will go to this point here. We go to 2 pi minus n omega maximum. And this area, this overlapping area, this one, is the one at which we have ideation. Okay, so what you want is that this is pi, right? This point here is pi. Okay, so you want that n omega maximum, n omega maximum is smaller than pi, smaller or equal, and at most it has to be pi. Because otherwise that is overlapping, because this copy here will invade our area, our minus pi area. And the same happens from the other side. Okay, so how would you clip your original spectrum here? How would you clip it to make sure that this condition is fulfilled? That the maximum doesn't go beyond pi. So you put a filter whose maximum frequency is pi over n. And then when you multiply by n, you are sure that it doesn't go beyond pi. So this is the anti-aliasing filter. Let's say that your signal is such that you still have so let's say that you go to pi. This is your signal, and this is x with omega. So our anti-aliasing filter is just taking, and this is minus pi. So our anti-aliasing filter is taking this area. And when we do the expansion, what we have is something like this. So x prime, let's move it. And this is 2 pi. This is 2 pi. This is pi. So we will have something like that. So this part is the one that is repeated. So we will have something that goes here, and then it is repeated. And this point is minus pi. Okay, so this area here is the one that is kept. And this, so a reminder, this is the anti-aliasing filter, and the expansion is done by the decimation. The decimation is the one that brings this point to pi. Okay, so now let's have a better perspective. So this is our whole procedure. Okay, so let's see now with images. With images, it is a bit more complicated because we have 2 dimensions rather than 1. Sorry. Okay, so yeah, so we have here the decimation. You recognize here the decimation. You are taking for an image, you are taking all the bands, and within each band, you are going from 1 to the number of rows, 1 to the number of columns, in steps of 2. So n is equal to in this example. Okay, then so this is the original image. This is the discrete Fourier transform, and then the decimated image will have a discrete Fourier transform that has twice fewer coefficients than we had at the beginning, twice in each direction, so it is 4 times. But so it is the same here. So you know that for any discrete signal, let's go here. So any discrete signal, let's make it here. I have a signal in real space. This is x of n, and it has a number of samples, and it goes to n minus 1, and then it has 0. Then the Fourier transform of this, how many samples does it have? The Lec15. One thing is the Fourier transform. Yeah, this is interesting actually. Let's represent both the Fourier transform and the fast Fourier transform. So these are related features, but they are significantly different. Okay, so now we go to the right. You know that I can represent the spectrum as we normally do from minus pi to pi, but it is equivalent represented in this way. Okay, so yeah, we go. So the Fourier transform it is this one. Okay, so it is continuous. What about the fast Fourier transform? The fast Fourier transform it is the Fourier transform but sampled at some particular points. Okay, it's 0, 1, and minus 1. So what I'm taking are samples in this spectrum. So those are related objects. So one is the Fourier transform. The Fourier transform of a discrete signal is a continuous signal. It is continuous in frequency. So if we think of this one is a function that goes from a continuous to complex. But this is continuous. This is continuous here. That's below. So this one is continuous. So it is a continuous function. But this one here, it is not continuous. This one is discrete. So this one here goes from the set of 0, 1. Let's make it more simple. So this one is discrete. Actually, it cannot take any different integer number. It can only take this one from 0 to n minus 1. Okay, but this is discrete. The fast Fourier transform is discrete. The continuous Fourier transform is continuous. Okay, so yeah, that goes to the point that this one here, the fast Fourier transform, that is the one that we were seeing before. So when we had it then, so we had an image and we have decimated it. So let's say that it has n samples on each side, not n, let's go R and C. R, and C. And now we decimate by factor 2. So now we decimate by factor 2. So it has C divided by N, R divided by N samples. So the Fourier transform, this one also has RC coefficients. This one also has now C divided by N, R divided by N. And both cover the same area. So both are going from minus pi or in the fast Fourier transform. They go from 0 to pi and from 0 to pi. And here the same. They go from 0 to 2 pi and from 0 to 2 pi. So we are covering the same frequency area, but now with fewer samples. So this is what we are seeing here. So this point is, we are representing from minus pi to pi, doesn't matter, we have. So we are going from minus pi to pi with this many samples. In the decimated image, we are going from minus pi to pi with this many samples that are less, are few. Okay. Okay, then we have a reminder of some property you may know, that is the scaling property of the Fourier transform. So let's say that you have an image, you have its Fourier transform, and now you have a decimated image. What is the Fourier transform of the decimated image? And then this property applies actually. Let's look at it. So let's write the property here. Let's go down. Okay, so we have something like, so we have an image of RC and it produces Fourier transform. I will do it with X, Y, find it more convenient. So we have Fourier transform omega X, omega Y. And now we do a decimated image. So we have NX. And we may decimate with different factors in each one of the directions, right? So what is the Fourier transform of this? So the Fourier transform of this is Nx and y, and then the Fourier transform of the original Nx omega x and y omega t. And this term here, let me check that I did not make right. So this term here is the one that makes the expansion. So it is the one that takes this kind of spectra and converts it into this. And this is happening by a factor nx in x, and it is happening the same by a factor ny in y. So this is called the scaling property. Scaling property of the Fourier transform. This you know, right? You know the scaling property, but in one dimension. Now it is happening in 2 dimensions. Yeah, this is also related to this uncertainty principle that we have all the time. So if something is wide in one space, it is narrow in the other. And we saw it in this example here. So in this example, we already had that. So which one is wider, the red one or the green one in real space? Which one is wider? Which one requires more samples? The green one. The green one is wider in real space. So which one is narrower in Fourier space? The green one. The green one is narrower. So the spectrum of the green is narrower than the spectrum of the red. So this is related again to this unsampling principle. And here we have a video showing that this aliasing, how it is shown, how it is seen in look at the wheel. It doesn't see. And the reason is this aliasing. So let's say that we have so let's say that we have the wheel that is moving at a given speed. So let's think of the spectrum of the wheel. Okay, so the spectrum of the wheel will have some frequency. Okay? So it has something that is. And then we do the sampling. So we do the sampling in such a way that, well, you know that, let's say that we have a couple of, so after the Fourier transform, after the sampling, what we have is the delta, and then we have another copy of this that appear at the frequency 1 over Tx, right? And then I choose 1 over Ts. So by choosing 1 over Ts, what I'm doing, or by choosing my sampling rate, what I'm doing is moving this copy in and out, right? To the left or to the right. And then I may choose it in such a way that the copies appear here. So we have this one. And I choose it in such a way that the copies are here. Actually, what is that? So let's say that this frequency is 1 over wheel. Sorry, this is not what I know. This is 1 over the period of the wheel. So if I make Ts equal to the period of the wheel, this is the pattern I have, right? And then at some point you are doing a low pass filter. So it appears that the wheel is fixed. It has 0 frequency. But actually it is not true. It is simply because of the sampling.
Hay un vídeo también de la puerta de la rueda.
¿El qué?
Hay un vídeo también de ese mismo una puerta de la rueda, el vídeo de un pájaro, no sé si lo has visto. Es un pájaro en una cámara de vigilancia y pasa lo mismo. Parece que no mueve las alas.
Sí. No solamente puede pasar que no mueva las alas, sino que si además, en vez de, por ejemplo, coger y hacer que este espectro sea, o sea, aquí lo he hecho iguales, pero podría haber hecho que, podría haber hecho por ejemplo, que mi periodo de muestreo fuera menor que el periodo de la rueda. Entonces lo que pasa es que la copia, aquí tengo mis copias originales, y ahora tengo mis copias que se mueven así. Esta sería la que está a 1 partido de S, pero tengo otra copia, que es la que viene de menos 1 partido de S, que ahí también se copia. Realmente esta copia se me viene aquí y aquí. Pero cuando haga mi filtro paso bajo, que yo no sé por qué lo va a hacer, cuando haga mi filtro paso bajo, parece que lo que tengo es una frecuencia muy baja. Incluso aquí estamos hablando solamente de frecuencia, pero si miro la fase, puede ser que la fase sea tal que en vez de que la rueda vaya hacia adelante, parece que la rueda va hacia atrás. Es un tema de fase. De hecho, me parece que en el vídeo este también ocurre. Ahora parece que va súper lento, pero esa rueda es un tema de sampling. Incluso a veces, eso, si miran la fase puede hacer que la rueda parezca que vaya hacia atrás. Bueno, venga, vamos a hacer un descanso. Okay, so let's continue. Okay, so here we have a representation of how these aliasing now look like in two dimensions. So let's say that this is the origin, this is the central copy, and we know that we have new copies appearing every 1/n in frequency. So this is the first copy, this is the second one, third one, and so on. And we have here the representation of why they may overlap and why we get an aliasing. Here is the spectrum of the train of deltas. Oh no, this is the train of deltas, so this is in real space. And they are separated by n samples. And you know, these are Kroneker's deltas, they are not Dirac's deltas, because we are all the time in discrete space. And then we are multiplying the input image by this train of deltas. This is what we get. So this is the sample image. So it is 1 every n of the input samples. And then this is a reminder of the convolution property. Buenas noches, Ana.
No ponemos 3.
No, uno.
Vale, viene un señor y le pregunta, pero oye, ¿por qué estás alargando las zapatillas? Y entonces coge y le dice, porque pone Converse. Mierda, tío.
Claro. ¿Os sabéis el chiste de bus?
No.
Suele pasar.
Busca en internet, no, cierra.
Mamá, en clase que me han despistado. No, pero si está en tu casa, Jaimito.
Hola. Okay, so this is a reminder of the convolution property of the Fourier transform, and this we already know. So convolution in real space translates into multiplication in Fourier space, and multiplication in real space translates into convolution in Fourier space. And here we are multiplying by the train of deltas in real space, so that is why we convolve in Fourier space. And this is the spectrum of the train of deltas. So it is here u and v play the role of the frequency. So we have omega x and omega y, and then the spectrum has a peak or a delta every with a separation of 1 over n. So that is why we get this repetition every 1 over n. Yeah, this you already know that if you convolve with an impulse that is shifted, then what you have to do is to copy whatever you are convolving to the location of the impulse. So that is why we have to convolve, we have to copy the original spectrum to every delta that we have in the 1 over n locations. So this is the same idea. So let's say that we have the Fourier transform of the original image is centered at 0, 0, and then we have to convolve with one of these deltas. So what we do is we copy, we shift the input Fourier transform to the location 1 over n. And because we have many deltas, we have many copies. Okay, so what is the condition that guarantees that we don't have any aliasing? So let's do it similar to what we had before. So what we had before is somewhere here. We had it. I think it was this one. So we have it here. So this one, we have to guarantee that. So that was in one dimension, but we have to guarantee that in both dimensions. So that the maximum frequency that you have in your original spectrum times n, because you are going to do the downsampling decimation by a factor n, has to be smaller than pi. Because later, when you do the decimation, it will be expanded by a factor of n. We saw this in this scaling property. So we are scaling the frequencies by a factor n. So to guarantee that we don't have any aliasing, originally the maximum frequency of the image has to be smaller than pi divided by n. This is the idea here. So if the support of the original image in Fourier space has a maximum radius, and this has to happen in all directions. So that is why we are talking of radius. So if we have a radius of 1 divided by 2n, then you are guaranteed that when you expand it, you don't have any aliasing. To n because okay. So now let's look at, for instance, let's say that this is our origin. Okay, so this is 0, 0. This is 2 pi, and this is 2 pi. So let's look at this square from 0 to 2 pi. So let's see what is happening there. Okay, so let's say that this is the original. This is the original. And we do a downsampling. So we can see it like this, we can see it like this, right? So now we make a downsampling by a factor 2. So if we make a downsampling by a factor 2, then this would be what we have. So every radius here will be multiplied by 2, so or by a factor of 1.5. So this radius goes to this point, but also this one enlarges by a factor of 1.5. The same with this copy and the same with all the copies. So this is what we get. And then you can do an Lec15 shift, for instance, of this signal. if you do the Lec15 shift of this is what you get. So you see that at the middle, there is a region that doesn't have aliasing. And this is what you expect. So when you have aliasing, you have aliasing at high frequencies. So high frequencies are in the surroundings or in the borders of this square. So you have the aliasing at high frequency, but you don't have the aliasing at low frequency. And the larger the decimation, if you make a decimation that is larger than this one, what will happen with this area free of aliasing? Will it enlarge or become smaller? So the more decimation you do, so if you take, instead of 1 every 2 samples, you take 1 every 10 samples, all these spectra will become larger. So all these will become larger by a factor 10 instead of a factor 2. So this area free from aliasing will be smaller. And then we want to apply first an anti-aliasing filter. So the anti-aliasing filter, we will crop the central area that has size 1/2n. So this is equivalent to in this Fourier transform, they don't have pi, so equivalent that we have, you know that the Fourier transform can be normalized in different ways. So there are many Fourier transforms. So you have the Fourier transform that is the one that we normally use, that is between -pi and pi. So omega. This is x. This is the one, but depending on how you normalize how you write the expression of the frequency, you may have one that is between -0.5 and 0.5, and -1 to 1. So there are multiple versions of the Fourier transform. And in ours, the anti-aliasing filter has to be defined between -pi/n to pi/n. But in his Fourier transform, it is 1. But the idea is that you have to, if you are going to do a decimation by factor n, you have to. The important thing here is not if it is, for instance, what would be, for instance, for this one, let's make, this is for the black. For this normalization, this would be 1/12, 1. And from this normalization here, but it doesn't matter. The important term is this 1/n. So all the time you are having 1/n, 1/n, 1/n. So if you are going to do a decimation by factor n, somehow you have to make sure that when you multiply by n, the frequencies they don't go beyond your limit. So that is important. So in all my explanations, normally I use this normalization with pi/n. But in his example, he has this one, in which the limit is 1 divided by 2n. Okay, so yeah, so first you multiply by this square, and then, so this is the anti-aliasing filter. this anti-aliasing filter is equivalent to convolving with something that has this kind of, well, it has some values, it has a kernel, we don't care about what are the kernel values there. Actually, if you have something that is a square like this, what are the values of this kernel? It's a sink. So if it is a step in Fourier space, then it is a sink in real space. Actually, it is the multiplication of two sinks, one in X and another one in Y. Okay, so yeah, so here we have the different process. So we have an original image with its power spectrum. Then we multiply by the anti-aliasing filter. So this will be the location of the anti-aliasing filter because we know that we are going to do a downsampling by a factor 2. So we will be keeping, and this is a reminder, we will be keeping this area, this central area. And in my presentation before, it was this one. Sorry. It was this one. So we are keeping this central area of the Fourier space, the one between minus pi n to pi n. Okay, so we keep that. So we set to 0 everything outside. This is the anti-aliasing filter, and now you can do the downsampling. And what if I use a different anti-aliasing filter? Because we know that ideal filters, they have ripples. They have these oscillations around edges. So to avoid those oscillations, we can use a Gaussian filter. So for instance, let's say we use a Gaussian filter with this shape in Fourier space. Is there a problem with this Gaussian filter? You are?
It will lose details.
Yeah. You are losing. So in the ideal filter, you are keeping this part, but in the Gaussian, you are removing the corners. So yeah. So let's see how it looks like. So yeah, we have this power spectrum. This is the power spectrum of the Fourier transform, the original image, times the Gaussian. This is how it looks like. And then we have reduced the ringing, but the result is blurry. So actually, this is the result. I didn't mention it, but this is the result with the ideal filter. So we don't have aliasing, but still the pattern looks a bit weird. And the reason is this ringing. So now we don't have ringing. We don't have ringing here, but it looks blurry. So instead of that Gaussian that was losing the corners, we can use a larger Gaussian. And now we don't lose the corners. What will be the problem now? We have a bit of aliasing. Because of this. These frequencies are not fully attenuated. So, so it is less blurry, but now we have aliasing, a little bit of aliasing. You can see the pattern here. So this is with the ideal filter. This is with the Gaussian that was smaller, and this with the Gaussian that is larger. And the decimation. So if you don't do any anti-aliasing filter, it is a complete disaster. You have a lot of aliasing. Okay, so yeah, I think that is all I wanted to say, because all this reasoning with torus I find them more difficult to follow. So yeah, let's keep the reasoning with the torus, and let's make the same reasoning, but now in terms of copies of the Fourier transform. So okay, so ideally, if this is the original Fourier transform, after the decimation of by a factor 2, I will have the central area. But this central area is contaminated with the nearby copies. And let's see how that happens. Okay, so actually I don't think there is a good, there is no good representation of this. So let me do it in the okay, so we have omega x with that very long and very low in this direction. We need more space. So let's say this is the area from minus pi to pi. And we will do a downsampling by a factor 2. So I will divide this in 4 meters. So this point is pi and a half, and this point here is pi and a half. This is omega y, this is omega x. And let's numerate all these. So let's numerate this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 16. Okay, but we know that we have copies. Okay, so let's make this copy here. So we have copies at 2 pi. And we have the same spectrum. So whatever is in this radio, we will have it there. So we have 1, 2, 3, 4, 5, 6, 7, 8. Now we have another copy there. And this is center of minus 2 pi. Okay. Now, and we would have more on the top, the diagonals, and everything. But I'm not going to go there. Just let's concentrate on this one. Okay, so now let's do the downsampling by a factor 2. So I have the original copy. Let me do it again. So this is our frequency space, this is the origin. And now we will do a decimation by factor 2. So this copy, instead of happening at 2 pi, it occurs at pi. Okay, so I have to shift the red copy to pi. Okay, so if I shift it, so shifting to pi means shifting it by 2 squares, 2 units to the left. Okay, so let us do it. So it is starting there, and now it goes here. So let's now let's write the red one. So it is 1, 2, 3, 4, 5, 6, 7, 8, And the same happens with the blue one. So the blue one now goes to here. So it will be 1, 2, 3, 4, 5, 6, 7, 8. So what we see is that in this area, we have some overlapping of the left onto the black. And in this area, we have an overlapping of the red into the black one. So that is actually why you want to do the low pass filter. So if you do the low pass filter, you do the anti-aliasing filter, then all these areas, they become black, they become zero. And then it doesn't matter if they overlap, because they are overlapping zeros.
But you lose information, don't you?
Obviously. But if you're decimating your signal, you're losing information. You're throwing one every 2 samples. Okay, so these are the patterns that are overlapping. So one is overlapping with 10. And we could do similar reasoning with the copies from the top, the copies from the bottom, the copies from the diagonal. And at the end, the patterns that overlap are somehow represented here. So, yeah, so we have the copy coming from 1, 2, 3, 4. And on top of it, we have this pattern 10, 11, 15, 5, 16 that we had in the slides. So look at this. Look at this segment now. So in this copy, we have 10 and 11 coming from the right, and 5 and 16 coming from the left. And this is what we have in here. 10 and 11, 5 and 16. And if you keep track of all the copies that are moving around, then these are the other patterns that you may discover. So at the end, in the central area, what you're having is a central area plus all these other copies coming from the surrounding copies that are collapsing onto you because of the decimation by a factor 2. But let's look at all these numbers. So these copies are 5, 10, 16, 11. So it is 5, 16, 10, 11. The other ones are 13, 14, 7, 8. So it is 13, 14, 7, 8. The other ones are 12, 15, 6, 9. So it is 12, 15, 6, and 9. So they are all in the high frequency area. So that is why you do the anti-aliasing filter. So if you first set all these extra regions to 0, and you keep, and then you do the decimation, there is no problem because you are overlapping zeros. So you have the central part of the spectrum plus all these extra information that goes into it, but they are made of zeros because of the anti-aliasing filter. This is clear? Yeah, and we have already been talking about this, that all the reasonings that you can do in terms of copies, you can also do in terms of a torus. So you can think of the spectrum, the 2D spectrum, like lying in the surface of a torus, and then expansions could be when you make, for instance, a decimation by factor 2, that we have said that the frequencies are multiplied by 2, then it is like expanding your function along this surface. Yeah, but the reasoning with the torus, I find it more difficult. This is the same idea. So which are the areas that are overlapping? So here you have the contribution. In this quadrant, you have the contribution from 11, from 1, and then 10, 14, and 12, and so on. Okay, good. And then, yeah, so the same with the torus. So there is nothing really new. Any question? No. Is it clear? These things are difficult. I understand. It is a matter of thinking of them carefully with time. Okay, so if there are no questions, then we move to the next topic, that is resizing images. And here what we will see is, okay, so this scaling that we have done by an integer factor, we have, for instance, make it smaller by a factor 2, by a factor 3 during the downsampling. And actually, we are not restricted to any integer factor. So you can do a downsampling by a factor 1.5 or 1.75 if you want. And for doing so, you will need something that is called interpolation. Are you, do you know interpolation from other topic? Any other course has talked about interpolation? No? None of them? Yes? Okay. ¿En dónde ha aparecido el telecomunicación? ¿En? Okay, so let's see the concept of interpolation then first. Okay, so wow. Okay, so let's define this concept of interpolation. So let's say that we have a continuous signal T, something like this, but you have some samples. So you have these samples here. So this is x of n. And then you have the axis n, and 0, 1, 2, 3. And in terms of time, you know, this would be 0, ts, 2ts, 3ts, and the sampling size is s. And this one is x of n/ts. So this is the general sampling thing. Okay, so let's say that we have the samples, and I want to know what is the. So all I have is x of n. This is what I have. I don't have access to the black one. It comes from the black one, but I don't have access to it. But and now I wonder. What is, I want to estimate what is, just to make things simple, so let's say that Ts is equal to 1, so that we don't have to figure out to deal with fractions and so on. So I want to know what is the value of the original signal at 1.5. So I want to know this value. But I don't have it. So all I have is the surrounding samples. So can I use the surrounding samples to estimate that point there? And there are many different solutions. The most simple one is this one. So I want to know it at this time. So I can join those 2 points with a line and evaluate that line at that point, at that time point. And that is called interpolation. So the process of estimating a function at a time location from nearby samples is called interpolation. And you may use just the two nearby samples because we have joined with a line that is called linear interpolation. So we're not crazy about names. So, we will come later, but I'm not restricted to just the two nearby samples. This is the easiest way to do it. But I could use the 4 nearby samples to somehow estimate what is the value there. So instead of just joining with a line, I could join with a curve, with a polynomial, for instance. I could join those 4. Let's try to be more clear. So I'm using the 4 points. So if I'm using 4 points, what is the degree of the polynomial? I have 2 points. What is the degree of this polynomial? This is a line. A line is a polynomial of degree 1. And if I have 4 points, I have these 4 points now. What is the degree of the polynomial? 3. So I can find a polynomial of degree 3 that goes through the 4 points, and then my estimate would be maybe similar, but a little bit different. And in principle, the higher the polynomial degree, the closer and closer I get to the truth. Is there any guarantee of that? If I increase the polynomial degree to a very large number, is there any guarantee that I will get exactly close to the black one? Sorry? Okay, but is there any guarantee that by increasing the degree of the polynomial, I will get closer and closer to the black curve? Well, it sounds reasonable, but is there any result that tells you that? The Taylor expansion, and you know that. So the Taylor expansion says that any function can be put as a polynomial of any degree not of any degree, but of an infinite degree. So it will be a0 plus a1x plus a2x squared. And what Taylor tells you is how to calculate these things. So those things are something like 1 divided by, I don't remember anymore the formula, but it is something like this. Something like that. So that is the Taylor expansion. Okay, so actually if I take an infinite degree, I get exactly the same black curve. So by increasing the polynomial degree, I get closer and closer to it. And again, we are not crazy about names. So the blue curve is called cubic interpolation. Cubic interpolation here. We are using a polynomial of degree 3. Okay. So this is what we will do. But we will do an interpolation of degree 0, that is a nearest neighbor interpolation, bilinear interpolation, an interpolation of degree 1, cubic and interpolation of degree 3. Okay, so yeah, so let's see this process a bit. Okay, so let's say that I want to make my image larger by factor 4 in both directions. So I start with this image. I want to make it 4 times larger. And I could do the following process. So I start with an empty canvas where I have zeros everywhere. And then this pixel here will be the 0, 0. So the origin will stay in the same place. So 0, 0 in my image, 0, 0 in my canvas. And then I take the 0, 0 pixel and I copy it to the 0, 0. And then I take the 0, 1 and I copy it to the 0, 4. And I copy the 0, 2 to the 0, 8. So now my original pixels become spread in my canvas, that is 4 times larger in each direction. And then I have to fill in the spaces. And this reminds me of this interpolation problem, right? This interpolation problem. So I have my samples. So I have my link samples. Then, so then I have this one, this one, this one. And what I want to do is just to fill 3 samples in between. So if I join with a line, those would be the 3 in between. But joining with a line is not the only way. For instance, I could say, okay, so I will copy the one on the left. So another way to fill it. So this would be linear interpolation. Linear interpolation. But I could say, no, I will join, I will fill the gaps. So these samples here. So I will fill the gaps with the sample that is closer on the left. So I will replicate this one 3 times. Replicate this one 3 times. So this is nearest neighbor, nearest to the left. Nearest neighbor interpolation. And if you think of Taylor expansion, actually this is A0. And this is A0 plus A1x. So I'm just taking the expansion of degree 0, the expansion of degree 1, and so on. Okay, so yeah, that is what we'll do. Okay, so we make a sum of that part. And now, for every sample, so those red points are the samples we actually have. And then the ones that are not with the red dot are the ones that have been copied. So this sample has been copied to the 3 samples on the left, and the same happens on the other direction. The 3 samples in the bottom, and then also this area has to be filled. So I take the same value and I copy it 16 times. And now it is like if I have a big pixel, so I convert every input pixel into a large pixel at the output. And then what if I want to go in the other direction? So instead of going from small to large, I want to go from large to small. This is the decimation operator that we had before with the downsampling. So you take 1 every n pixels. So if this is the input, then I will take a sample 1 every 4 pixels, and I'm leaving just the 3 pixels that are in between, and I'm leaving them out. Yeah, so those are the samples I have to keep, and then I will put them into my output. Okay, so this way of making images larger or smaller, they are called nearest neighbor interpolation. It is an interpolation of degree 0. And here we have some examples. So let's say that we have this input image, and then this is a zoom, and we can make a reduction by a factor that is not an integer, like 3/7, for instance. But for doing that, we will exploit these two operators. So the two operators are making it bigger by an integer factor, so going from small to large by an integer factor, and also going from large to small by an integer factor. And if you want to go 3/7, well, what you have to do is to make it larger by a factor p and smaller by a factor q. So we will do that later after esto. Bueno, mañana el examen y al otro también, luego ya Semana Santa. Os pondré en Semana Santa en el team. Me tenéis que mandar una pregunta de los vídeos de Dios. Espero que lo estéis siguiendo más o menos. Y entonces os diré, pues me tenéis que mandar para el día tal una pregunta de los temas tal a cual.